This paper presents a physics-informed learning solution for friction modeling on robots equipped with electric motors and high-ratio harmonic drives. We introduce a comprehensive pipeline that includes data acquisition, pre-processing, ground truth generation, and model identification. This versatile pipeline can be applied to all joints of a humanoid robot. By generating desired motor current trajectories, we can control multiple joints simultaneously. The data collected from these experiments form the dataset for friction identification. To model the friction, we use a physics-informed neural network, which inputs the history of joint velocity and position error between the joint and motor. To validate our solution, we use a two-layer torque control architecture that integrates friction compensation based on the identified model. We compare the effectiveness of the physics-informed neural network model by analyzing the tracking of a high-level task against the performance observed when using two standard static models, Coulomb-viscous and Stribeck-Coulomb-viscous. The first experiment focuses on tracking a sinusoidal trajectory on the ankle roll and the knee joints. The effectiveness of each friction model is assessed by determining the lowest KP, ensuring the tracking of the desired trajectory, and it is obtained with the PINN model. For further validation, we use the lowest high-level controller gain with all the models. In the case of the standard static friction models, the estimated friction is inaccurate, and the high-level task is not tracked. The same experiment is run on the knee joint. As in the previous case, the lowest controller gain for tracking of the joint sinusoidal trajectory is obtained when using the PINN model for friction compensation. Also, in the case of the knee joint, we repeated the test using the lowest gain found from the previous experiment, and a good tracking is guaranteed only when using PINN model. The next experiment aims to maintain a constant position of the joint while applying an external disturbance. When the contact ends, the controller will return the joint to the desired position. As previously demonstrated, the controller cannot correctly return the joint to its initial position when using the classical static friction models for friction compensation with the high-level controller gain that is suitable for the PINN model. For the final test, we repeated the same experiment on the knee joint. We applied external disturbances, while the high-level controller aimed to maintain a constant joint position. Similar to the ankle joint, when using the static friction models, the controller could not achieve the desired task. Although higher gains improve performance, they introduced instabilities. However, with the PINN model, the task was successfully completed while maintaining low high-level controller gains, thanks to more accurate friction compensation. Thanks for your attention.